As a first example of the grand canonical ensemble, we consider the ideal gas. We will use the classical partition function lambda of alpha, beta, and v given by the sum on all number of particles n from 0 to infinity e to the minus alpha n times 1 divided by n factorial h to the power 3n, and then integration on the 3n dimensional phase space e to the minus beta p squared divided by 2m. We see by comparison with the canonical ensemble that the second term, including the phase space integral, is nothing else canonical partition function z depending on n, beta, and v. Now, taking the result from the canonical ensemble and inserting into the sum that the grand canonical partition function is given by the sum on all n, 1 divided by n factorial, the volume of the system, e to the power alpha, lambda thermal to the power 3, all to the power n. The sum is nothing else like the definition of the exponential function. Hence, the grand canonical partition function of the ideal gas, lambda, is given by the exponent of volume divided by e to the alpha and divided by lambda thermal to the power 3. Having the partition function, we now calculate the conjugate variables that will finally lead to the equations of state of the ideal gas. Let's first consider the derivative of the log of the partition function with respect to the affinity alpha. Well, this is the mean number of particles and is given by v divided by e to the alpha and lambda thermal to the power 3. Now we can rearrange our result and explain the mean number of particles as just the number of particles. We can express alpha as a function of the volume, number of particles, and the thermal de Broglie wavelength, or in terms of the chemical potential, we obtain mu is equal to kBt ln n times lambda thermal to the power 3 divided by the volume. This latter expression we now use for the interpretation of the chemical potential mu. In case that the thermal volume of all particles given by n times lambda thermal to the power 3 is equal to the volume, then mu is equal to 0. Yet if the total thermal volume of the system is larger than v, then mu is positive, or when it's smaller than v, mu is negative. The mean energy of the system is determined by taking the partial derivative of the log of partition function with respect to beta. Now we do here an intermediate step by first taking the partial derivative with respect to lambda thermal and then the internal derivative of the thermal de Broglie wavelength with respect to beta. Using this trick, the partial derivatives are easily solved, and what we obtain is that the mean energy of the system is equal to 3/2 mean number of particles times kBt, the result that we obtained earlier. Likewise, for the last conjugate variable, gamma, which is equal to beta p, is given by the partial derivative of the log of the partition function with respect to v, yielding mean number of particles divided by the volume. Now, rearranging this last expression, we obtain back the ideal gas law that p times v is equal to the mean number of particles times kBt.